Hi, and welcome to ENSC 3231 Lab 5. My name is Abby Oakes, and today I'm going to be conducting a flow characteristic analysis on a used single-serve coffee machine. This coffee machine's endured daily use for about a year now, and it does not have a filtration system in it currently, and it also has not been descaled. So we're going to see what effects the deposits have on the internal mechanisms and how that affects the flow. The first thing I'm going to do in this lab is collect measurements for the inner diameter of the coffee pot holder, the outlet diameter of the coffee pot holder, and the pipe length for the hose on the inside of the machine. That I'm going to have to do in a non-destructive manner. I watched a YouTube video previously, and I'll be talking along how I am deciding to measure that, so I don't have to take the entire machine apart. I'll also be gathering the water temperature for later measurements on dynamic viscosity, and the brew time and fluid volume output will be measured for each of the cup sizes. I'll take 4 data points for each cup size. With that said, let's get started and measure the inlet diameter for the coffee pot holder. I'm going to turn the machine off to do this, so hopefully it isn't too hot. I cleared the machine of coffee grounds before conducting this experiment. And I need a flashlight to measure this. So I have a ruler here, and the measurement for the inlet diameter, it's a little bit hard to get. I would say that is 0.6 centimeters. Yeah. We'll log that down. Next, I have to remove the coffee pot holder to measure the outlet. And this still has some grounds in it, so I need a paper towel real quick. Okay. So it's hard to see it from this distance. I don't know if the camera will pick it up, but there's a crosshair in between the outlet holes for this configuration. So I'll need to take the diameter for the outlet itself and then the thickness of each of these crosshairs, so I can deduct that from the area. The outlet diameter is 0.7 centimeters. But the crosshairs they have a thickness of 0.1 centimeter. Next, I'll be measuring the assumed pipe length within the machine, or the assumed hose length that the water is traveling from the reservoir on this side of the machine to the needle in the top of this, which feeds into the coffee pot holder. chamber. So to do that, I'm first going to explain what I learned from a decomposition video. The reservoir has an outlet hole in the back bottom corner over here that feeds into a check valve, and then that feeds into a pump on this side of the machine. I'm going to assume that the outlet is about 5 centimeters above the bottom of the machine. So I'm going to assume that the hose is going to come out of the top of the pump and not the side, because they're going to want to keep their hose waste to a minimum. So measure about 5 centimeters up on this side, and then it has to go up into a tank somewhere in here. This is a hot water tank. I'm going to completely neglect the fact that there's a hot water tank inside the machine, because the viscosity, the surface area is less, and there's less fluid in contact, and I think we can get away with considering it negligible. And then that hot water tank feeds up into around here, and it has to cross over, and this extends, the piping extends about a thumb length below in the middle on the top here. And then that has to come up to here, and then it feeds to the needle right here. So I'll take all those measurements, and then we'll get started with the flow for each cup setting. So 5 centimeters is right here. And I'm going to assume that this goes to all the way up here. We're going to neglect the water tank. Actually, let's assume, yeah, that the pump is 6 centimeters now that I'm looking at it. Takes up 6 centimeters, so the hose should be, it comes to the middle here. Let's say 15 centimeters. Then it has to cross over all this direction in the middle. So that's going to be about 5 centimeters across. Has to come up about the length of a thumb in here in the armature. So just my thumb is somewhat short, so I'm going to go ahead and call that 7 centimeters. Then it has to come up in the armature, and then from where it exits the top here into the armature to the needle in the front here is according to the video decomposition I watched, it will come to about 10 centimeters. However, in order to help account for slack within the machine, I'm going to go ahead and say that it goes all the way out to where the needle is at 15 centimeters. I'm also going to assume that there is some extra slack in the machine, probably because where the pump is and where the water tank is. I'm going to assume that there's about this much slack in the hose because it's not going to run straight into it. So we'll take whatever the circumference of this is. So pi d divided by 2, pi times, let's say 11 centimeters. So pi times 11 centimeters divided by 2. Of course, all of this will be converted into meters later. So I'm going to start the flow analysis with the 6-ounce cup setting. We'll be taking 4 data points, and I will be using the stopwatch on my phone to find the brew time for each cup setting, each data point. After taking the brew time, I will check the fluid volume output for the machine and log it down below. From the brew time and the fluid volume output, I can later calculate the volumetric flow rate, Q, the mass flow rate, m dot, and from the estimate of pipe length or hose length within the machine, I can find the pressure drop using the Darcy Weisbach equation in my later analysis. I can also take the mass flow rate or the volumetric flow rate equation and find the flow velocity, and then use that in the Reynolds number calculation, because I was kind of curious about whether the output is laminar or turbulent. So we'll find that out. And lastly, I will document, take some photos of the flow for each cup setting, and just see if I can determine any interesting novel flow characteristics from the photographs taken for each of those cup settings. That said, let's begin. It is something to note, for the first 2 cup settings, I'll be using this Pyrex cup. It has 25 milliliter markings. So I tried a mock lab before this, and this seems to work okay. However, for the 10-ounce cup setting, I am using this larger measuring cup, which also has milliliter marks on it. I'm not sure if there is any inconsistency in this, but this is what I had on hand, so I have no graduated cylinders. All right. Now for the 6-ounce cup setting, I will be pushing the button and starting the stopwatch at the same time for all of these. And also, when I'm considering the brew time to be off is when the light goes off on the machine. As it like switches off and switches over, it will still be dripping a little bit, but it won't affect the volumetric flow rate calculation much because it's not that much fluid volume afterwards. Okay, and start. Okay, so the brew time for that 6-ounce cup setting was 33.15 seconds. And the fluid volume is going to call that 170. 170 milliliters. Actually, let's do 100 and, yeah, 170 milliliters, that would be fine. I have a bucket over here to pour the excess into. It is worth noting that there are still some coffee grounds in here somehow. So that might affect the volume a little bit for that reading. But we'll be taking 3 more. This is just the second one. Never mind. We'll just not take that one because I forgot the start button. Okay. Okay, it's still heating, so I have to take it when the heating light goes off. Yeah. .86 seconds. And the fluid volume output is a little bit higher this time. It's right below the 175 milliliter mark, so let's call that 173 milliliters. I can only really get accurate to 2 significant digits, but I can kind of tell which one's higher and which one's lower. So the third one is even more so, the third digit is even more so of a guess. Okay, trial number 3 for the 6-ounce cup setting, and start. 32.92 seconds. And a fluid volume output of 174 milliliters. Not very different from the last measurement. Let me turn this around so you all can actually see the lights for the rest of this. I can use it this way. Okay. So this is the last run for the 6-ounce cup setting. And 33.13 seconds. That one was significantly longer than the last two, so let's see what the fluid volume output is. Let's say 172. That one might be a little bit lower, but I'm not getting much variation in the fluid volume output this time. Got more variation when I ran a mock trial for this yesterday. Okay, so now we'll be starting the 8-ounce setting, the 8-ounce cup setting, and taking the brew time and fluid volume output for that one as well. We'll do 4 data points, just like we did for the 6-ounce setting. Okay. Reset the stopwatch. Set that and start. 42.02 seconds for the brew time. And the fluid volume output is just below 225 milliliters, so we'll call that 224 milliliters. It is worth noting that this is the 8-ounce cup setting. However, just like yesterday, I am getting less fluid volume output than the company would specify should be output. This is less than 8 ounces. It was also less than 6 ounces and less than 10 ounces when I ran the mock trial for this lab yesterday. We need to refill the tank, and we'll do the other 3 trials. 42.13 seconds for the brew time. Fluid volume output is bit more than 225 milliliters. We'll call that 226 milliliters. Eight-ounce trial 3. Start. .06 seconds. Fluid volume output is solidly on the 225 milliliter line this time. Now for this last trial for the 8-ounce setting, I'm going to put a temperature thermometer into the cup, and we'll take the temperature reading for the dynamic viscosity, so we can know what temperature to get the dynamic viscosity of water at. Doing it now so that the cup is hot, so it's not losing, the fluid isn't losing heat to the cup as bad as it would have been at the start of this experiment. Okay. This is the 8-ounce cup setting. And start. 182 degrees Fahrenheit. The brew time was 41.93 seconds. $227 milliliters. And that concludes the 8-ounce cup setting trials. Next, I'll be moving on to the 10-ounce cup setting. 50.30 seconds for the brew time. Fluid volume output is 280 milliliters. There's really no way to guess the ones digit on the numbers for this larger measuring cup, as it only has designations between each of the 50 milliliters. Okay. Trial 2. I was getting variations of 12, 13 milliliters yesterday when I ran through some of the data. I'm not getting that large of variations today for some reason. $49.63 seconds for a 10-ounce trial 2. I'm going to try to get a temperature measurement again and discard the first one because I think the temperature should be higher than I recorded for the 8-ounce measurement during the 8-ounce measurements. So we'll try that again this time. Needs water. Let's stop that. Okay, and start. Let's get this right in the fluid stream reflected this time. Really about 176 this time. I'll go ahead and take the 182. It's actually 182.0 degrees Fahrenheit the first time. It's 49.58 seconds. And okay, yeah, wow, this is the variation I was talking about. I have about 360 milliliters this time. Yeah. I'm going to discard my second trial because I forgot to log a fluid volume output for it. So I'm going to discard that brew time and do 2 more trials. .84 seconds. For the fluid volume output of 200 and actually exactly 300 milliliters. And the fourth data point, the last data point for the 10-ounce setting. After this, I'll run through each of the cup settings and take a few photos of the flow profile with outlet. Well, maybe not profile, just outlets. .76 seconds. The fluid volume output of 200 and let's call that 280 milliliters. Okay, for the last thing I'm going to do for this lab is take some pictures of the flow at each cup setting. See if we can see evidence of turbulence, laminar flow. Because of the way the fluid outlet is, it causes some flow separation, which makes it look turbulent. We'll find out if it actually is turbulent or laminar after the analysis. But I'm going to take pictures of the flow anyway, so we have kind of an idea of what it looks like for that particular Reynolds number that we calculate. On that one again. I need to take I'm going to take pictures of that again because that was blurry. So. Okay. I'll try it for the 8-ounce cup setting. And then finally the 10-ounce cup setting, and that will conclude the lab. Lastly, we have the 10-ounce cup setting. We can take a visual record of the outflow. And with that last piece of documentation, that concludes this lab. What we've covered here is applicable to many circumstances in reverse engineering if you are a fluid mechanical engineer who deals with fluid mechanics on a daily basis. Some companies employ based on how well you can find this information and put it to good use. So I have the brew time, the fluid volume output. I will follow by calculating the volumetric flow rate and the mass flow rate. We'll use the internal estimate for the hose that I did earlier to place into the Darcy Weisbach equation to find the head loss or pressure loss due to viscous effects. And I can use either the mass flow rate or the volumetric flow rate to find the flow velocity and calculate the Reynolds number for the flow at each of these data points. That concludes this lab. Thank you.